Hello everybody, welcome to my YouTube channel, which I've now renamed Theoretical Physics with Mark Weitzman. Today I want to do a problem in Srednicki's book, finish lesson 4. So this is lesson 4, the spin statistics theorem. And this is the part 4 video on problem 4.1 in Srednicki. This is my solution. And the integral that we're going to evaluate was used to show illustrate problems with causality and scalar fields and how cancellations occur and everything. But for now, the problem is just the evaluation of a standard type of integral. Remember D.T. Kilder's Srednicki's notation for an invariant measure. We want to show that this is equal to m over 4 pi squared r k1 mr. K1 is a modified Bessel function of order 1. Now, since the, remember that d tilde k is equal to d3k over 2 pi cubed 2 omega k. Omega k is equal to the square root of k squared plus m squared. So, and we also want to verify the limit as m for a massless particle as m goes to 0. Now, since the integral is manifestly Lorentz invariant, because we have the Lorentz measure, and everything else is just products of 4 vectors. Srednicki suggests we evaluate in a frame where t equals t prime, and also we are treating the case. So we're treating the case of a space-like separation where x minus x prime squared is defined to be r squared is greater than 0. Okay. Now, so that means the integral becomes the integral of d3k 2 pi cubed e to the I k dot x minus x prime divided by 2 times the square root of k squared plus m squared. There's 2 ways of evaluating this. One way is the way we're going to do it, which is in spherical coordinates. In momentum space. And then the other way is Peskin and Schroeder. I think it's on page 27. Use the contour method. And that's also elaborated by Stanny Danny Strands, who has these notes, which I've posted on my Piazza website. It's like 2,000 pages of notes, and he does it there. So if we look at I'm sorry. If I look at here, this is Peskin and Schroeder, page 27, where they evaluate. I don't show more, but this guy has like 2,000 pages of notes, a lot of which follows Peskin and Schroeder, and he does this integral in great detail, giving you references to the digital libraries for the Bessel functions and everything. So you can look at this also. Here are the contours. And so this is another thing to look at. And let me just get back to doing it in spherical coordinates. So in spherical coordinates, the key is to trick is to align the KZ axis with x minus x prime. We can always choose our coordinate systems, and we can choose it so that the z-axis aligns with this vector. So now the integral becomes the integral of d3k over 2 pi cubed e to the I k dot x minus x prime. I'm just rewriting this 2 square root of k squared plus m squared. This is equal to the integral from 0 to 2 pi of d phi, the integral from 0 to pi of d theta, the integral from 0 to infinity of dk k squared sine theta e to the I kr cosine theta divided by the square root of k squared plus m squared. Just to show you this trick again, if we draw a little diagram, this vector over here is going to be x minus x prime. This is the kz axis. And then we're going to have like theta. And this is the k vector. K is equal to the absolute value of k. This is our coordinate. So this is the phi coordinate. There's no dependence. Will give us a factor of 2 pi. This is the theta. The k, the measure, is k squared sine theta. And the dot product of the vectors is just magnitude of one times the magnitude of the other times cosine theta. So that's very easy. Now in evaluating this integral, we get 2 pi divided by 2 pi cubed. The integral from 0 to infinity, I'm changing the order a little bit, dk k squared 2 square root of vector k squared plus m squared, or that's just k squared. So I have, then I have minus e to the I k r cosine theta over I k r from 0 to pi. As you can see, it works out real nice because when we take the derivative of this, we have an IKR, which cancels that, and then we get a minus sine theta. The minus sign cancels, and then we get the sine theta that we want. So it all works out nice. This is equal to 1 over 4 pi squared r, the integral from 0 to infinity, dk k. Remember, a k cancels, so we lose a power there. K square root of k squared plus m squared, e to the ikr minus e to the minus ikr divided by 2i. And this is equal to 1 over 4 pi squared r, the integral from 0 to infinity, dk k square root of k squared plus m squared sine kr. Okay. So this is what we worked it out to. Oops, sorry. Now, if we want to cheat, and substitute m equals 0 to get the limit right away, we end up getting 1 over 4 pi squared r, the integral from 0 to infinity, dk sine kr, which is not defined, doesn't converge. What we can do is we can use convergence factors. And or heuristics. After all, we are theoretical physicists. Here. So what we can do, rather than, you can do the convergence factors, or you can just integrate it directly, and you're going to get 1 over 4 pi squared r, the integral from 0 to infinity, dk sine kr is equal to 1 over 4 pi squared r minus cosine kr divided by r, taken from 0 to infinity. And then you can argue that average value of cosine kr at infinity is 0. And that will lead to 1 over 4 pi squared r squared, which is correct. Okay, so that is sort of a just an aside. We'll do it more rigorously, although I'm not really sure it's actually more rigorously. Now, to evaluate the integrals and get the Bessel functions, you can use, I did this a long time ago, so I used what I own. I can't even pronounce these Russians' names, but they have a famous, 1980, I think they got a 5th edition now. This was 4th. I had it at Caltech. It was a very cheap book. And page 419, 3.7542, number 2, has a nice formula, the integral of 0 to infinity, cosine ax over the square root of beta squared plus x squared is equal to k0 a beta. And you can see that over here. This is that book, page 419. I put a red mark. I'll have these pages in my handwritten summary posted on my Piazza site, but this is the equation that I'm using. One can also use the digital library, online digital library. Very convenient nowadays, very thorough. It's dimf.nist.gov, National Institute of Standards, and Digital Library of Mathematical Functions. Their number is 10.32.11. I'll just show it to you here. This is the digital library, and they have Bassett's integral. And if you put nu equals 0 in this, you'll get what we want. And the same thing as what was in the Russian book. So, same as G/R when nu equals 0. Okay. Now taking this formula, what you can do is use Feynman's differentiate with respect to parameter. And in this case, that would be the parameter is a. So we can write dA, the integral from 0 to infinity, cosine ax dx divided by square root beta squared plus x squared equal dda k0 ab. And that leads to the integral from 0 to infinity, x sine ax divided by the square root of beta squared plus x squared is equal to beta minus beta k0 prime ab. And now we just got to figure out how to manipulate derivatives of Bessel functions and various orders and everything. So my suggestion is to use, if you don't remember these things, now use your favorite math methods textbook. In my case, I use Matthews and Walker. And I'll show you that. So this is Matthews and Walker and the two formulas that I use right there, underlined. Okay. So using those two formulas, I'm going to get, and doing the case where m equals 0, I'm going to get, and they, even though they're written in terms of j, they apply to k, because after all, k is just linear combinations of various other Bessel formulas or of imaginary arguments. So equals that. And the other one was, we also get k minus 1x plus, I'm sorry, equal k0 prime x. So these two imply that k0 prime x is equal to minus k1x. That's, you could probably do it by directly if you remember what the definitions are and everything. So now, substituting that above, I have the integral from 0 to infinity, x sine ax over the square root beta squared plus x squared dx is equal to beta k1 a beta. Okay, so now going back to our original formula, substituting in, just taking into account the different letters, I get e to the I k dot x minus x prime divided by 2 square root k squared plus m squared. This is equal to 1 over, we showed it was equal to 1 over 4 pi squared r, the integral from 0 to infinity, dk k sine kr divided by the square root of k squared plus m squared. By the way, like the k in here is a 4 vector, and this is a 3 vector, but Lorentz covariant, this is just the magnitude of the 3 vectors. Okay, you just gotta slide with the notation. This is equal to m k1 mr divided by 4 pi squared r. So that's what we wanted to show. We verified that. Now let's take the limit as m goes to 0. So here, I don't know, asymptotics, I found it easily in Jackson, classical. You can use the digital library too. Second edition, page 108. When x is much, much smaller than 1, k nu x is equal to gamma of nu over 2 over x to the nu. So when nu equal 1, we get k1x goes to 1 over x, and this goes to 1 over 4 pi squared r squared, which is also correct. So as I said, you can do this in Peskin and Schroeder. The notes, Feynman, I also have it. Feynman in his 1962 QED pamphlet book. Also does it, and I'll include that in the written material. He doesn't give the details, but I worked it out. If you look at, there were the relevant formulas in Jackson's book. And then this is Peskin and Schroeder. This is Feynman's QED book, where he calls it I plus, and he evaluates it in 2 different ways. Where he gives the result, a Hankel function, and then he does another expression. And my handwriting, I show how to do it with the contour that he's using, and I evaluate it. And we get the same answer. So that's the end of this problem. It's a short calculation, but it's a standard one on the spherical way that I did it and the contour way. It's good to be familiar with both of them. And it's nice to have a lot of books and a library where you can get things, although nowadays you can go to that digital library. Not so easy to search these things, just like it's not so easy to search these 1,000-page books with all the integrals, but sometimes you got to do it. Anyway, thank you for watching, and I'll continue with Lesson 5 next time in Srednicki's book. Bye-bye.